Hi everyone. In this video, we're going to be discussing section 5.4, which is about how to calculate probabilities for multiple dependent events. So, in the last lesson we talked about independent events, and we'll find that that was actually a simpler case of calculating the probabilities for multiple events. But dependent is just a little bit more involved. And to begin with, we're going to introduce the idea of a conditional probability. And so the notation we use when we talk about the conditional probability is this. We say, what's the probability of event 1 occurring given that I know event 2 has already occurred? So we use a little vertical line to separate event 1 and event 2. And again, the way you read this out loud, if you see this notation, you read this as the probability of event 1 given event 2 has already occurred. Okay? And the way that you would calculate this, you calculate this by saying this probability, this conditional probability, is equal to both the probability that event 1 and event 2 happen, divided by the probability that just event number 2 happens. Okay. So know that formula. And I'm going to show you a couple examples of conditional probability, because I know sometimes when you just see it in abstract, when you just see the formula, it doesn't really click as well. So here's our question. What is the probability that a randomly selected male is widowed? And I'm bringing back this contingency table. I think I've used this in a previous lesson as well. This is a contingency table. And the columns then represent male and female. And the rows represent different marital statuses according to the U.S. Census. And we're asking, what's the probability that a randomly selected male is widowed? So event 1 would be like, that the person is male, and widowed would be event number 2, right? And so what we're asking is, what's the probability that we find someone widowed given that we know that they are male? Okay. Well, if we know they're male, we're only going to look in this column of the contingency table. And we're asking, what's the probability that they're going to be widowed? And so this is going to be 3.3 out of however many males there are in this. And so I'm going to definitely need a calculator for that. So I'm calculating the total number of males. That's 46 plus 63.3 plus 3.3 plus 12.1 plus 2.2. So 126.9, if I did that correct. 126.9. And so we just divide 3.3 by 126.9, and that's how we get this particular conditional probability that we're asking about. And so with the contingency table, it's actually very easy to see and calculate conditional probabilities. So here's a new example for you. What's the probability that a randomly selected divorcee is female? And so I'm going to consider as my space in my little sample space, all the divorced people. And I'm wondering, among the divorced people, what proportion of them, what fraction of them are female? And so the probability of being female, given that we know they are divorced, would be this. Say female being event 1 and divorced being event 2. And the probability of female, given that we know they're divorced, that's going to be 16.1 over the total number of divorced, which is 28.2. Right. So again, conditional probabilities are pretty easy if you see the contingency table and you read the question very carefully and you know what you're asking, right? Because if I reverse this and I asked you, what's the probability that a randomly selected female is divorced, that's a totally different number. So make sure you know what the question is asking. That's probably the biggest mistake we'll see on the exams. So here's the multiplication rule for dependent events. Remember, in the last lesson, we learned the multiplication rule for independent events. But we are actually concerned in this lesson for what's the deal with dependent events. And so this is just the slightly more complicated rule, again, because this time we're concerned with this conditional probability. We're saying that, hey, for dependent events, E1, the fact that E1's occurring actually does affect E2. So the probability that E2 is going to occur is actually going to be different given that E1 has occurred. And so that's why you see the conditional probability appear when, for independent events, that conditional probability simplifies to just being the probability of event 2 occurring. Well, now we have to worry about that conditional probability. So let's talk about reaching into a bag of M&Ms. And E1 is that the first M&M we draw in it is red, and I actually have to come up with some numbers, so I guess I forgot to. But let's look at the number of red M&Ms over here. I see 1, 2, 3, 4, 5, 6, 7, 8. So we'll say that there's 8 red out of a total of, man, and I don't really want to count all these M&Ms, but let's say that there's 30 total. So the probability that the first one that I draw and eat is red, that will be 8 out of 30 as a theoretical probability. And now the probability that the second M&M I draw and eat is red, given that I've already eaten one of them, that's going to be 7 out of 29, isn't it? Because I've removed one of the red M&Ms and I've removed one of the total M&Ms. So now, if I want to calculate the probability of both of these events occurring, so if someone asks you, what's the probability that the first 2 M&Ms that we draw and eat are both red, well, this would be 8 over 30 times 7 over 29. That's going to be 56. No, I said 56, which was correct. I wrote 59, which is not correct. Over whatever 30 times 29 is. So that's going to be like 870, I think. Yeah. Somewhere around 870. Yeah, I think that's it. Okay, so this, and maybe you can simplify that fraction, but this is our probability that we found for these 2 dependent events to both occur, right? Okay. New example. Let's say you have a standard deck of 52 playing cards and you're dealing 2 cards out of that deck. And event 1 is that the first card we're going to deal is a diamond, so it belongs to this suit, one of those 13 cards. And E2 is that the second card I deal is red. And so dealing a diamond, the probability is 1 out of 4, because there's, diamond is 1 suit out of 4 possible suits. Typically, the probability that the second card I deal is red would be 1/2 for the probability of E2 occurring, right? But these are not independent events, but these are actually dependent events. And so what I'm concerned with is just not the probability that a card I draw out of a full deck is red, but actually the probability of drawing a red card given that I've already dealt a diamond. And so the remaining number of red cards is going to be 25 red cards, given that I've already removed one of the reds. And the total, I'm going to have 51 cards left to draw from. So the probability of E2 given E1 is 25 out of 51. Now I want to ask you the question, what's the probability that the first 2 cards are first a diamond and then second any of the reds? Well, that's going to be 1/4 times 25 out of 51. So this is going to be 25 out of like 204 or so. And this fraction you can't simplify, as far as I know. Let's see, the factors of 51 are 3 and 17, and 25 is just 5 and 5. Yeah, so this is actually the simplified fraction for that probability. Okay, so new example. You randomly select an individual, and we say E1, the event is that they have a college degree, and let's say there's a 40% chance a randomly selected individual has a college degree. And let's say that the probability that they have an annual salary greater than $50,000, given that we know that they have a college degree, is like 0.6. Well, then the probability of both of these being true, so you randomly select an individual with a college degree and an annual salary greater than $50,000. This is just going to be 0.4 times 0.6, which is 0.24. Okay. Oh, and that's actually the end of my slide deck. So it is the end of the video, and I will see you guys in the next one.